Okay, so new topic, states of matter. On the left you have solid, and on the middle here you have liquid, and then far right here you have gas. The bell work was asking students to compare the picture on the left with the picture on the right, and what you should have gotten was that on the left here you have solids. And on the right here, you have a gas with the smoke. And then I went further and said, what's the difference between the Jello and the bowl that it's in? Well, the Jello has particles that are loosely packed, whereas the bowl has particles that are tightly packed. Okay. The kinetic theory of gases has only 3 components, but they're only valid at extremely low densities. And the reason for this is because if they were at high densities, they wouldn't behave ideally. And what we are talking about in this topic would be hard to understand. So, point number 1 with the kinetic theory of gases is that a gas is composed of particles, usually molecules or atoms. We treat them as hard spheres. Well, we know that these hard spheres are called atoms, but for the sake of this topic, we're going to call them spheres. Insignificant volume. Well, it's not insignificant, but we call it insignificant because with gases, they always fill the shape of the container that they are in. And so you could decrease the size of the volume of the container, or you could increase it, but you would still have the same amount of gas particles in there. Okay, and then also they're far from each other. So we know that gases are very spread out. Second point of the kinetic molecular theory is that particles in a gas move rapidly in constant random motion. And we know that the gases don't go in one streamlined position, that it's random. They're just bumping into other gas particles, and the motion is always constant. If it wasn't constant and the particles slowed down, then you would not have a gas anymore. You'd have a liquid or a solid. And finally, number 3, all collisions are perfectly elastic. Well, the picture down here, it was a moving picture, but all of these particles here were running into each other and then bouncing away from each other. And it's elastic. It's an elastic collision when 2 particles come together, and then they hit each other, and then they bounce straight back. Now, it would be inelastic if the particles came together and then they stuck together and didn't go anywhere. In junior high, middle school, maybe even in biology, you probably talked about kinetic energy in some form, but the kinetic energy is just the energy of motion. The energy an object has because of the motion. So when a gas is heated, it absorbs thermal energy. When it does this, because of that absorbed energy, what it does is it takes that thermal energy and it converts it into kinetic energy, which increases the speed of the gas. So when you heat up a gas, it starts moving faster. As a substance moves from solid to gas, the kinetic energy increases. Well, that makes sense. If you know that a solid's particles are very tightly packed, they don't move a whole lot. Solid is fixed in place. When it goes to a liquid, the particles begin to move faster, and they slide past each other, and then eventually with gas, the particles go super, super fast. The average kinetic energy of a gas is proportional to the Kelvin temperature. Well, we learned about this term proportional here in class, and basically what that means is that when one of them goes up, another one will go up. In this case, if kinetic energy increases, well, the temperature is going to increase. Okay, vice versa. If you were to change it, if temperature increased, kinetic energy increases too. So it's proportionally related. So down below it says particles at 200 Kelvin have twice the kinetic energy of particles at 100 Kelvin. So basically, if you have 100 Kelvin and you decide to double it, if you double it to 200 Kelvin, well, what's going to happen is that the kinetic energy is also going to be increased twofold. The Kelvin temperature scale is used because 0 degrees Kelvin is the temperature at which all motion ceases. And so 0 Kelvin, theoretically, the gas molecules would come to a complete halt, would not move anywhere. So we use this scale because it covers the whole range. This picture here just illustrates that. You have gas in a container moving at a steady speed, but what you do is heat is added here, and that thermal energy, again, okay, will be radiated into these molecules, and they will pick up kinetic energy, and that's what it shows here. You have these longer tails showing that the gas is moving faster. We get gas pressure when gas particles collide into objects, whether it's a balloon container or a classroom or wherever. As long as there's gas, there's going to be pressure built up because of the collisions that it has with another object. So in this picture, we asked where the pressurized areas were of this. And in this case, a lot of people would have said that, all right, well, it's going to be in this balloon here. Well, technically, the pressure, once it's equalized throughout the container, it's going to be the same throughout. You're going to have pressure against the wall here, here, against the liquid, against the cork. Some of it's going to travel through the balloon, and you're going to have pressure exerting on each wall here. So there might be more gas particles in the balloon after it expands, but that's only because it's stretchy. It doesn't mean it's more pressurized in that area. The same pressure is being exerted everywhere in the flask. Atmospheric pressure is something that you might be familiar with. It's the pressure caused by the weight of the atmosphere. It decreases with an increase in elevation because the atmospheric gases are less dense. If you can imagine taking a bowling ball and maybe wrapping a sheet around it, the gases in the atmosphere are heavy and they lay over the Earth like a blanket. As you get further and further close to Earth, the gases get more dense, they heavier, they stack on each other, and as you go farther away from Earth's crust, the air begins to become what we call thin. There are less gas molecules that are in the air. And keep in mind, gases are like CO2, nitrogen, helium, hydrogen, some inert gases like neon, argon, krypton. They're all in the atmosphere. As we get higher and farther away from Earth's surface, the air gets thin. Okay, it's more dense towards the surface at sea level. The question was presented, so what happens with atmospheric pressure when you're in the mountains? Is the pressure higher or lower? Well, when you're in the mountains, we talked about getting farther away from Earth's crust. The gases become thin. There isn't many gases. There's a lot of gases stacked at the surface of the Earth, where the sea level is. But when you're in the mountains, the pressure is going to be lower. There are fewer air particles pressing on you. When you are further down at sea level, say you're at Houston or Galveston near sea level, the gases are stacked up heavy down at the bottom close to Earth's surface. And so you feel more pressure. We may not feel it a whole lot, but it's there. The gases are pressing in on us more than they are when we are up in the mountains. This is an instrument used to calculate atmospheric pressure. It's called a barometer. And the way it works is that you have air pressure that is pushing on around this pool of mercury. Now mercury, symbol Hg, is a liquid at room temperature. And what happens is this atmospheric pressure, whatever it might be, say you're in the mountains or down at Houston, it's going to push the mercury up this tube. And depending on how high it goes, the higher it goes, the higher the atmospheric pressure is. The lower it goes, the lower the atmospheric pressure. We have 3 units of pressure that are important. The first one would be the Pascal right here. It's the SI unit of pressure. SI also meaning things like liters, grams, seconds, moles. Pascal fits in there. The second one that we have is millimeters, Hg. It's equal to torrs. Those are kind of the same. And then finally, we have ATM, or atmospheres. Okay, and this happens at STP. or at STP, you have 1 atmosphere pressure and 0 degrees Celsius. We talked about this in the stoichiometry and mole conversions when we were going from a gas to moles, using the conversion factor 22.4 liters per 1 mole. In this case, we're looking at pressure. And so we have 1 ATM. So 3 units, pascals, millimeters, Hg, and ATMs. Millimeters Hg is the pressure needed to support a column of mercury 1 millimeter high. So that barometer we looked at in the last slide, that's where millimeters Hg comes from. So overall, what do you want to take from this slide? Well, you want to take away this green text here. These are conversion factors, okay, and these are going to be used when we are trying to convert pressures. We might be given a certain pressure, and we want to go into something else. So you use these conversion factors to go from one type of pressure into another. So summary of what we talked about. Well, number 1 here, gases are composed of particles that are considered to be hard spheres. Okay, so that's one you want to pick up. And then also, it has little volume. So again, gases can be compressed or they can be expanded. So basically, if you were to put all the gas molecules close together, it wouldn't take up a whole lot of volume. That's why it says little volume. Number 2, right here. These particles are spaced far apart from one another in constant motion, and I should say constant random motion. And finally, number 3 here, they collide in perfectly elastic manner, and I should say perfectly elastic manner. Energy is never lost. We're going to be dealing with an equation, several equations, but different variances of each one. But there's going to be 4 main variables that we look at. Number 1 is pressure. V is going to represent volume, T for temperature, and then N, number of moles. So number of moles here we had looked at last 6 weeks in stoichiometry, and so we're going to use these skills again when we're involving moles within our reaction. Or sorry, not our reaction, our equation. Compressibility is a measure of how much the volume of matter decreases under pressure. So we can compress gas and we can confine it to a smaller and smaller and smaller space, or we can continue to expand our container space and decompress the gas where it expands and gets larger. So what happens when you add or remove gas from a container? Well, if we add more gas to a container, okay, we're going to increase the number of particles. We're going to increase the number of collisions, and we're also going to increase the pressure. So I like to think about it as a classroom. And the classroom is your container. And the gas particles are the students. So basically, in a classroom, if you add more students, if you add more gas to a container, what's going to happen is, obviously, the number of students, the number of gas molecules are going to increase. The number of collisions inside your classroom, if you have a bunch of students, there's going to be collisions. Students are going to run into each other if you have a bunch of students in the class. And if that happens, students are going to get angry, and you're going to start increasing the pressure of your classroom. Students are going to feel a lot of pressure. They want to move around. Kind of a tacky analogy, but works for me, so I hope it works for you. But the pressure of the container of gas will increase if you add gas to it. So same thing goes if you remove a gas from a container. If you take away students from your classroom, you get rid of them, what's going to happen is you're going to decrease the number of students. Duh, right? Well, you're also going to decrease the number of collisions. A lesser amount of students, well, you're not going to be running into each other as much. And you'll be able to go about your business if you're a student in the class. You're not going to feel as much pressure, so the pressure of the container decreases. Again, I know, tacky analogy, but let's roll with it. So let's look at pressure and particles again. The number of particles of a gas and pressure are directly related. So here comes this word again. We talked about proportionality before. Now we're looking at directly. So those words mean the same thing. So directly or proportional means that when one goes up, another one is going to go up. Okay, so in this case, we're looking at pressure and gas particles. So if we double the number of particles, we're going to double pressure. Both of these will increase together simultaneously. So the visual down here, we start out with a container. It's got a certain number of gas. What we do is we add gas. And what happens, you'll notice that this lid goes up. And that's because there's increased pressure in here. So now we're going to compare two different variables here. We're going to change the size of the container. So we're going to look at volume, and then we're also going to look at pressure. We looked at pressure before. We're going to look at volume again. So in this case, if we increase the volume of our container, if our classroom gets bigger, there's not going to be as many collisions in our classroom. There's not going to be as many collisions between the gas molecules in a container. So what's going to happen is the pressure is going to decrease. Okay. Vice versa, if you cut your classroom size in half, if you cut the container size in half, well, you're going to increase those collisions with each other and the walls around them, and the pressure inside that classroom is going to increase. So a visual down here, this was moving where this piston here would compress and squeeze the particles together. So we're going to look at this graph, but if volume is high, there's not a whole lot of pressure. And what we saw was that as volume goes down, pressure will begin to increase. So that piston went down and the gas molecules became more and more concentrated, or not concentrated, compressed. And so volume might be low, but the pressure is going to increase. So we like to call that indirectly related. Volume and pressure are indirectly related. So basically if you double one, so basically if you increase one, the other's going to go down. In this case, if you increase volume, pressure is going to go down. Okay. So if you half one, the other will double. And we'll look at examples like that. And one final relationship that we need to look at is the effect of heating or cooling a gas versus pressure. So we're going to look at temperature and pressure. So if we compress a gas, it says compressing a gas increases its temperature, and expanding a gas decreases its temperature. So if we heat a gas, what's going to happen is that heat, that thermal energy, is going to be absorbed by the gas molecules, and the kinetic energy is going to increase, which means the molecules are going to start moving around faster and faster. And when that happens, you begin to start having more collisions within the container, and those collisions cause pressure. So if you heat up a gas, you're going to increase the pressure. So if you increase the temperature, you're going to increase the pressure. So two up arrows, that means that these two variables are directly related. If you double the Kelvin temperature, the pressure is going to double. Cooling a gas, complete opposite. If you decrease temperature, you're going to decrease pressure.